Okay, welcome. Lecture 29, and we'll go through our slides here. Let me get my screen stuff all organized. All right, as I was saying a moment ago, we're going to try to wrap up the second module of our kind of advanced function topics today. We'll do a bit more review on lambdas, since I think those are really important for you, and they will be on the final. So we'll do a little bit more practice with those to try to get the syntax in your head. But here's where we are. So we're just going to finish out on the functions. We're going to pick up and talk about exceptions and probably asserts as well on Thursday. Not a big topic, but a good one that you should have seen and understand the syntax. You'll also see those on the final as well. And then next week, we're going to just try to fill in one lecture with software patterns. Software patterns is kind of the advanced discussion when we get into design. And so we'll give you one or two of those. We'll play around with some practice stuff, and then we'll just kind of dedicate Thursday to final exam review. Couple of reminders. Of course, everybody knows that quiz 6 was due last night and homework 8 also due last night. So we're kind of into the penalty phase of homework 8. I hate to call it that, but so get those in as quickly as you can if you're finishing those up. And of course, we'll be here tonight to help you, or anytime you have questions. And so here's our objectives for today. We're going to go through a couple announcements. We're going to review very briefly the syntax for functors and function pointers and lambdas just from last lecture, so we kind of get you familiar with that again. And we'll just do some more exercises on those. Wanted to make sure, since it's such a strange syntax, that everybody has a chance to play around with that a little bit, ask some questions. And then we're going to look at variadic arguments. This is variable arguments in functions. And there's two fundamental ways to do that we're going to look at. It's kind of a problem you run into every once in a while. One of them is variable arguments using kind of an old school library. Pretty straightforward, but a little clunky as well, and limited. And then variadic templated functions, which is very crazy stuff. But very, very powerful. Both of these approaches would let you have a variable number of arguments in your function, something that C isn't super straightforward in dealing with, like some other languages are, predominantly because it's a compiled language. So final exam, because some folks had asked about this. It is going to be an at-home one, obviously. No one's coming in. It is going to be at a very specific time. There's going to be a password, all the usual stuff. It will be timed, so it's going to be as if you're in class. It is going to be open book. I thought about leaving it closed book. There's a number of people discussing this, and every instructor, I think, is going to take a different approach. But I think, to be fair to everyone, we'll just make it open book. You can prepare yourself. It's going to be, there's going to be a few more questions than I otherwise would have, because the idea is not that you can spend forever researching all this stuff, but you have some retention. So you're going to have 170 minutes. At the most, I think you'll have 75 questions. So it's going to be just a little over 2 minutes per question. So obviously being prepped for this is going to help you. My goal is that you don't need to go look things up. Open compiler. Yeah, for sure. Yeah, I mean, but to be fair, if there's a question about, if there's really a different answer based on the compiler, then, we'll have a discussion about it after the fact. The right answers should be, common to multiple compilers, at least as far as all the questions have been designed. But yeah, you can use your own compiler. But yeah, the idea is these things you should be able to discern them by, understanding the semantics roughly and the meaning behind the question. I don't imagine a lot of you, I know you want to check your answers, I get it, but you may be a little bit pressed for time. So as with everything, my goal for you is to just be exercising your brains on this stuff. So even, I hope you are learning in the process of taking the final exam, regardless of how you go about doing it. So this is 20% of your grade. So it's kind of big, as you know. It's going to be multiple choice and true false, and it will be cumulative. So I will be reaching back for some things in the earlier part of the semester, but since we kind of built up, it's definitely going to be leaning more into the new material, because the new material will incorporate all the old stuff as well. So And as before, as with the midterm, it's going to be based on quizzes. So, you know, if you literally look through your quizzes, you will get a strong sense of what those questions are going to be like. And then there's going to be some extra stuff that I'm just going to put, I'm going to try to collect the stuff that we've covered since homework 6 and put it into what I'll call, since we covered since quiz 6, and put it into a quiz 7, non-graded quiz 7. So you can just, if you have the time and the interest, you can practice with that a little bit. It just seems fair to give you that practice. And then additionally, I am going to do a practice exam like we did before the midterm. Again, the whole focus is just on repetition, because that's how you get good at this stuff. If you are still struggling, it'll give you a chance to go back and ask yourself those questions. I'll try to get all this stuff out by next Tuesday's class, the practice exam and the quizzes. Worst case, I'll have the extra quiz stuff, which I'll just call it quiz 7. I'll have that out. It's ungraded, but I'll have that at least by Tuesday, and then it may take me a couple of days to just get the final exam practice, the final exam out. So that's the final exam. Any questions on that? Okay, cool. Hopefully that gives everyone a good chance at reducing their stress level going into this, and a lot of chances to learn more stuff, which is all good. So here's the stuff that would fall into this ungraded quiz 7. So this is just a collection of the things we have talked about or we will have talked about that were never on any quiz before. And you'll get a chance to see what I mean by this, but this is the only thing that's sort of kind of an outlier here. Basically, we've seen so much syntax inside of classes so that, you know, I feel like if I give you a prototype and I say, hey, what is this? Is it a constructor? Is it a destructor? Is it an overload for a greater than sign? You should be able to pick out from multiple choice to tell what that particular piece of code represents. So you'll have an opportunity to practice that on this quiz 7. It's also in the Outlook, the Quizlets, which I'll remind you of once I put out the quiz 7. So there's multiple ways you can practice that. And then of course, all these other things, we're kind of covering all of this right now. So that should give you really, really good clarity on the new stuff and then all of the old quiz stuff. And then you'll have the practice exam as well, okay? So I think that's that on the quiz. Homework 10, I mentioned this before, just reminding you again, if any of you find that you're kind of on the threshold and you had a bad homework assignment and you think this might help you, I'm going to be pretty, reasonable about grading this. I know everybody's got a lot of stuff going on. So if you submit me a game that matches these criteria, I'm gonna, give it a, reasonable interpretation. So if you can demonstrate that you're utilizing concepts that we've talked about, and approach it from the standpoint of a game, you don't have to do it. Obviously, I'm just going to throw out the lowest grade, but I wanted to mention that again. And if you could just, let me know that you're going to do this, give me a heads up. I can be thinking and watching for what's coming, because these things are always going to take more time for me to grade. So I just want to prepare. But not critical. If the last minute you realize you need to do it and you're going to do it, then that's okay too. Okay. Any questions on all that stuff? Okay, great. All right, well, let's do a little review. I know this stuff is a little tedious sometimes, but just to make sure we remember, we talked about functors last time, which is how we use a class to make a fake function. And the nice thing about, because we know with classes, they don't really exist until we instance them, and that allows us to instantiate a function. That instantiation allows us to, in the way that we create an instance of a class, to feed it something via the constructor. So like in this increment class, we have a private inc value, which is how much are we going to increment something? And our constructor sets that up. That's part of the creation of our function, which is the functor. And then the instance has the overload for these two parentheses, which allows us to create the function signature, or the arguments that are part of the function, right? So we looked at that last time and tried a few examples on how we would do that, and pretty straightforward once we remember kind of what these overloads are doing, right? And we've covered that a few times. So we create an instance where we increment things by 5 or by 3. All of those are just instances of the class. Now, it is true that although we would invoke this function via an instance, we can create transient instances of classes. Like I could say increment capital I, parenthesis, feed it some constructors, and pass that result, or follow that result, or that's created without naming the instance. I could follow it with a pair of parentheses, and it would still invoke the function. But it's a very transient way, and not very standard. So generally, we call these functions from the instance, not from the class, right? You have to create an instance in order to actually invoke the function. That's the really key thing to remember there. Okay. So those are functors. So a couple of quick test questions. Is a functor implemented via a class? Well, yes, you should remember that. Is it a specialized syntax? Not really. And by that, I mean, it's kind of a strategy. There's no keyword functor that you could look up and find out where to put it in your code. Definitely, we are not overloading the equals sign. A number of people understandably get confused about that sometimes. But the key thing that we're overloading, of course, is the parentheses. So these are just the big bucket things you should know. And you can, although we've done exercises with one argument, you can put as many in there. It's just like any other overload. You can pass a bunch of arguments into there. Okay. And like I said, we generally will call it from an instance, even though you could create a transient instance like we do sometimes when we're assigning something like a token. Some of you in your jigsaw puzzle were creating transient instances of the token class without ever assigning it to an instance name. That's okay, you can do it. But it is creating an instance. And what you do with that instance is up to you after that. But otherwise, yes, when we create it, once we create it, we just call it like a function, right? In terms syntactically, we really don't really have a way of knowing immediately that it's not a function just by looking at a little snippet of code, okay? So they're useful because they can be instantiated when you need them, and there's some customization that we can apply to the functor when we instantiate it so that we can create different flavors of functions. That's the key benefit, okay? Any questions on functors? Cool. All right, function pointers. Also, we didn't do a ton of stuff with this, but just looking at syntax. So we kind of tried to, because the syntax is sometimes so confusing, I try to introduce it in various forms, right? So this is declaring a variable, we put it in simple terms, called FP, and that a variable is a function pointer. It can store the address of a function. And the function that it stores is a function that returns an int and has a string as an argument, for example, right? So here is a function that returns character, passes in a string, right? Says char, but it's a string, sorry. And then this is just a function with no arguments, or sorry, this is a pointer to an integer. Ha, almost caught myself there. Right. Yeah, that you'll probably see on the test. And then here is, of course, the difference, right? The key differences. We have the parentheses on that. Okay. And let's see. Also, a couple more arguments, right? So this is, I mean, the key thing here is that these pointers, as with so many things we've seen in C++, are very type sensitive, right? It has to exactly match the function signature that we're talking about, right?
Professor, I have a question.
Yes. Mm-hmm.
Just to double check, the pointer name, the function pointer name, and the pointer need to be in parentheses?
Yes, they do. Yes, absolutely. I'm cool. Double check, but I feel pretty sure they have to. And we know, I mean, normally we wouldn't do this with an int pointer. I did this really to just kind of move you through the formation of the function pointer, but obviously this FP here doesn't need to have the parentheses on it. That we've seen before.
Yeah.
Okay.
Yep.
Cool. All right. So then let's see. So just a quick thing here. So here's say it function. We create a variable named myfunc, which matches that function signature. And now, of course, we can just assign it. All right. So, and then call it. which is pretty straightforward. But if you've never seen it before, it might be a little mind blowing to think that you can pass that thing around and then invoke the function with some arbitrary variable. Very nice to be able to do that. The next thing we talked about was lambda expressions, really a big topic. And I think I mentioned too, it's quite cross language. So lambda expressions are, the concept of a lambda is kind of everywhere these days. It's a really transient, fast way to write a function in a very tight syntax. Unfortunately, a little cryptic. But it's just very convenient and often is used inside of function parameters. You just need to write a function right there in the midst of some set of function arguments, this other function you're calling. And people do it. If you haven't seen the syntax before, I can throw you a little bit. So it's important to get a little bit familiar with it, right? And we can name that lambda. So this whole thing right here is the lambda. We can assign it to this name f or whatever. And as we mentioned, auto is always the type we use if we're going to name a lambda. If we're not going to name a lambda and we're just going to create it, use it, and throw it away on the fly, then we can just leave out all this cyan colored stuff here, right? So that's the optional part. And the capture is very powerful, but somewhat confusing. It doesn't have a super strong corollary to functions, but it does have a corollary to the functors, which we just talked about. When we create an instance of a functor and we pass things into its constructor, that constructor of that functor is very much like this capture clause. And if you read up on lambdas, they'll tell you, and at least in major compilers, they're implemented via functors. And so that's very likely what's happening is this capture is going right into the constructor for a temporary functor that's being created behind the scenes. But otherwise, we have our standard function arguments, and then we have our return type here out at the end, which is a little annoying because usually we have it in the front, and then our implementation over here in the braces, okay? So we have capture. And then a couple powerful syntaxes we didn't really look at for capturing all local by value or all local members in the current scope, right? In the current scope in which the lambda is defined, right? So those might come in handy, okay? So we looked at a bunch of that, and we'll do more of that today just to make sure everybody remembers that. So here was an example, kind of a complete example. I kind of name this lambda here, and I pass in Q, and I capture Q right at that moment, so that if Q were to change later on, right, I change Q to 100 and I call the lambda again, it's still going to use the Q that was used when I essentially defined this, right? When I named it, it got captured, right? So we saw a little bit of that.
I have another question, Professor.
Yes.
You say local variables are what you put inside this capture clause, but the question is, you can't even put like members or stuff you get out of a function or anything?
So they have to exist essentially on the variable stack in the scope in which the lambda is created. So at this point in the code, when I say auto, this lambda equals Q, Q has to be defined somewhere, and its value would have been presumably set. But you couldn't say, like, you couldn't throw in something like an instance of a class dot member, right?
Mm-hmm.
I
see. So you have to like kind of put them through that local variable.
Exactly.
Yeah.
They have to be kind of bound to the local scope in some way. I mean, there may be, I don't think honestly, you can capture an instance that way, like, because, if the instance is in the local scope, like if Q was actually an instance of some class, then we could capture Q there. But it would have to be existing in this space. Because remember, we don't put any type information. We're just sort of echoing the exact same name that existed in our wrapped scope, the scope around where the lambda is created.
I got you.
Yeah, it's weird. I mean, the equivalent in JavaScript I've used, probably quite a bit more than I have in C++, and you can get in some crazy situations when you pull in all of that local scope. And often, sorry to go on, but it usually you capture excuse me, the scope, so that you can maybe pass this lambda to some other thread, right? So if you think about our thread execution we talked about a few weeks ago, essentially thread is like somewhere else altogether. It's off on its own execution line, and you might need, and it has no way of reaching back and getting scope or anything like that, right? It's somewhere else altogether. So if we can capture something and pass it in, then that thread has access to a whole lot more information, without having to declare all these variables and things like that. So that's just one way you might use it. Okay, cool, good questions. So right, so there's our name. We talked about auto, our arguments, return value, right, and the Q capture. Okay, so that's our lambda. We'll do more of that today. So we're going to do, to start off, we got about 6 exercises. Oh, right, let me load up. I'm going to load up the links again for anybody that might have missed it. This will just take a second. Links. All right. Okay, so at least you have that. Let me know if anybody has any troubles. So we're going to practice these along with, I think we looked at for each. So we'll do a couple more of these. We're going to look at accumulate, which might twist your mind a little bit in good ways to make you think about these things a little differently. And then we'll kind of write one or two a little more elaborate lambdas, and then we'll move on to variadic templates. Okay. So here's the idea with these for eaches, and I think everybody's got this by now, but it does confuse people sometimes. So bear with me while I do this visual here. So the idea is that you've got some iterable container with a bunch of stuff in it, and you've got this for each function, which is a nice utility function that's just going to walk through. You give it the beginning of the iterator and the end of the iterator, and so the for each is going to hand over one by one, right? It's going to hand over each member of that container to the function that you give it. So you notice we gave it foo here. So basically for each is just handing each individual item to the foo one after another, right? Just going to pass it in as the first argument. So there's something implicit here in for each. It's expecting you to give it a function that accepts one and only one argument, right? Unless you've maybe defaulted the third and fourth argument to something else, right? So that's the key thing with for each. It's going to just call your function with one argument at a time. And that's it. And then what you do with that is entirely up to you. It doesn't really give you any other way to directly do something. And we'll see with accumulate, there's some other stuff that we can do here. But that's basically what's happening. It's just calling it with the equivalent of C of 0, C of 1, etc., all through those different members. Okay, so you could print stuff, you could maybe store it in a database, you could do a whole bunch of things, or launch a bunch of threads maybe. Yeah, you might decide that this is a bunch of threads in your game that you're going to spawn right off at the beginning, but they're in some container, and you need to call it. Oops, sorry, that's my PowerPoint slides talking. That's a little spooky, actually. Okay, so let's go on then and look at how we might do this with a string-based container. So here's our names. We create a lambda here. We're going to name it print me, right? We're going to pass in a string. There's going to be an empty capture here. And all we're going to do is print out that name with a comma and then pass this to the for each. So for each is just going to, fire through all those names from begin to end and pass it to print. Pretty straightforward. Now we could have, as we saw, I think on Thursday, write a transient lambda, right? Rather than naming the lambda, we could also just shove it all right in here. It's kind of a mess. We could shove that whole lambda function in there between the parentheses as the third argument of that for each. Totally fine to do that if you want. And it goes away without a name right after that execution happens, okay? Same thing, okay? Just looking at that again for an integer. I think you guys all get this by now, but there's another one we could do, or we could do it in line like that, okay? Hopefully that all jives. So, so we're gonna do this with a transient lambda, and we're gonna have you guys write one, put it in the for each, and what I want you to do is try to send in with your transient lambda a capture of a character. So when we print this, and I think you can run this function, you'll see that it just prints all these words end to end. There's no space or comma or anything in there. So your job is to kind of finish this program, of course, and just introduce any kind of delimiter you want, so that your worker function, if you will, that we're getting passed in there, your lambda, will print that delimiter. So rather than having Mickey, Donald, Goofy, you have Mickey, comma, Donald, comma, etc. Whatever, depending on the delimiter that you pass in. Okay, so so give that a try. I think this is going to be super quick, but it'll kind of serve to dust off any rust that you might have gathered over the weekend. And let me know if you have any questions on that. I'll give you about 2 minutes on that one, and then we'll talk about it. Okay, go for it. Oh, sorry, I missed that question earlier. Let me just catch it up. Right, exactly. Yeah, Jackson's right there. You can either through a lambda capture or through a good old functor, you could pass something in. I mean, obviously you could do tuples if you wanted to inside of your container if you wanted to get a little fancy there. But we'll see as we move to our accumulate example, we'll see something a little more complicated, like maybe what you have in mind there, David. Good question. I'm just going to take a peek at the solution here and see if I right. So I left you, of course, I left you the transient lambda is started. So you just have to fill in the capture there. Okay, pretty straightforward. Let's take a look at that. So you could do this any one of a couple ways. You could create a string delimiter variable like that, right? And then inside of your for each, just kind of drop it into your capture area there, right? And so now we have the opportunity to see out S and delim. And you might think that's an argument of the function, but it's not. We've just captured that local variable and brought it into that lambda, right? So that's how we would do that. And you could bring in as many of those as you want. You could comma separate them. You could use the equal or the ampersand there, as we saw, to pull in everything, which probably is not a good idea to do by default unless you really need everything. But you can do that. Okay. Any questions on that one? There was kind of a follow-on question of, how would we go about doing this if we didn't have the lambda? And this is a rhetorical question. It's like, well, we could have written this print strings function, right? And which we've done before, right? We, of course, would think to just write a function before we knew about lambdas. But the question is always in your head as the designer. It's like, well, is it worth it writing this function? Am I going to use it again? Is it a big function? Am I wasting a lot of time? You get to decide. I'd say it's kind of right in the margins right here on this particular example. If you were calling it a whole bunch of times, it's probably a lot smarter to just write a function like this or name the lambda than to actually just keep doing that syntax in line all the time, because eventually you're going to create some sort of a mistake and create a bug, right? So we always want to write code once if we can and reuse many, right? So it really depends quite often, okay? And just a little FYI, probably we haven't looked into C14, and I haven't looked at this specifically in C14, but we can't do templates on lambdas. Sometimes that question comes up, or we can't do it in C11 if we move to C14.
Ah, shoot.
Yeah, sorry. Yeah, that's sarcasm, right?
Oh no, it's actually it
Oh,
would be really cool.
oh, okay, okay.
Yeah.
Oh yeah. No, that's yeah. It's pretty powerful stuff for sure. Yeah. Yeah, but man, I tell you, I'm not sure I'd want to look at a full page of templated lambdas that in
Yeah.
someone else's code. I mean, it's not a bad thing. It's like it's some stuff you got to digest. Okay, so we're gonna step it up a little bit and try to actually literally replace the for each with a lambda here. Okay, so the idea is that we have some vector of values, and we have, you know, we would have this function print me that we would pass in, but we just want to keep the print me and rewrite the for each with a lambda. Okay. So we want to be able to say, you know, my for each, which is really the name of a lambda, pass in the v, and then call some pre-written print me, right? That's traditional print me function. All right. So this is just meant to, you know, give you a little head scratcher. So give that a thought, and consider that the print me function is done. And so you're going to need to write a lambda expression that basically does that, right? So give that a try, and I will jump into the code here. You will probably need to declare a function pointer in your lambda argument so you can receive the print me function. So we're kind of combining two things that we've recently learned, function pointers and the lambda here. Okay, and then give it a call from main. So you're going to define it in main and then call it in main. That's the thing about lambdas, is we can write them, we can write functions inside of scope from main or some other function, which is nice. Okay. And then if you want, you can try to replace the print me with a lambda if you get this done early enough and you feel like you've got a handle on this, but you don't have to do that last part. So give that a try. I'll kind of jump in the code and narrate a little bit and ask me any questions. Okay. Just looking for any gotchas there. I, of course, wrote the print me for you. So I guess I cheated a little bit here if this point is confusing. If you look at the way we're invoking our lambda, my underscore for each, we're really just passing it two arguments, right? It's not exactly like the for each where we're passing in the iterators. We're just passing in the name of the container. So your container argument declaration for your lambda, your named lambda, will end up being a vector of int, right? And then your second argument will have to be a pointer to a function that passes an int, right? Because you are going to print an int. Yeah, that's what the print me does. Okay, that's a couple seconds, and we'll take a look at the code. The nice thing about these is they fit on one line. You know, it's kind of good and bad. They fit on a PowerPoint slide a little easier. Okay, let's see what we got here. So I think I broke this up a little bit. So here is the for each, right? So the name, no capture. We pass in as our first argument the container in my kind of bastardized version. And then here's my function pointer. That's going to be our print me function that gets passed in, right? And here we'll do an iteration through the begin end. Now you could have done it exactly like the for each, and I probably should have to make this a more straightforward example. But if I was going to do that, then I would need to declare a begin iterator and an end iterator, and then my third argument would actually be the function pointer. That would make your Lambda a little more of a general purpose function, just like the way the for each is. But you could certainly do it, right? And then we just call the function, right? We're just calling that argument, which is a function pointer, with the Q, right? With the pointer to, or with the dereference rather, to the iterator. So we actually get what's in the container, okay? So that's how we would write the for each part, right? And then we could call it like that, like as designed. So that part was already written, right? Pretty straightforward. And then if we wanted to rewrite that, that's pretty easy to do, right? We could actually just say my for each v, and then replace the print me entirely with our own little packaged Lambda there, okay? So yeah, very, very concise, very compact, a little hard to read, but once you understand how to break it down, eventually your eye begins to pick out these brackets. It's like, okay, we got a Lambda coming here. And then you have to figure out where the implementation is and look for the function signature and a return value, which might happen in here. But and we may not get that good at this at the time that we have, but that's just our introduction to it. So I won't go through all this really slowly, but for Lab 28, this is just my recent attempt to try to give you guys a little more extra stuff to play with sometimes on the side. So I talked about this one on Thursday. So the idea was just write some lambdas to compute some stats, typical stuff. And the idea was to iterate through some container and just print those things out. And don't name them, just like write them, write the lambdas and just, have them be gone. So we were going to try to do the sum, the average, the median, which typically is going to require that you pre-sort those things rather than try to do it in the Lambda, unless you're going to write a Lambda that sorts containers. That would be kind of ninja Lambda stuff. And then the statistical variance and print out the primes. That stuff was a little involved, but I thought I'd throw that out there. So here's the code just so you can see it, right? So, so this one, you should be able to guess what these do now by looking at the code. So I'll just give you a moment to think about what this is. If I were to give you this on a quiz, for example, or final exam, you might say, you probably would say, hopefully, that that's going to print out all members of the all values container, right? You're going to be iterating through those with the for each. And although this might be confusing to your eye, this is the matching parenthesis, of course, for the for each. So we're just, spatially opening up this area so we can articulate the Lambda in a more traditional function form, right? But that's all that's really happening there, right? So here's another one. So let's look at this. So we've got something captured now, right? I start out with something called double sum. That's a big hint, obviously. And then I capture that, right? And it's captured by reference. And I'm passing in an I, right? That's coming in from the for each. So for each is dropping in one of the doubles every time we come through this all values container. I should have had a declaration for that above there for clarity. But I'm passing in the I and then I'm summing. Yes, go ahead.
I have a question about for each with the all values being the last slide before this.
Okay, yep. Let me go. Bear with me. Focus on the right slide here. Yep.
How do they know how to use I? How do they know to use I?
Well, so we are calling it I. So, we, the writers of the Lambda, decide that our Lambda variable is going to be called I. Just like any function, we get to call our own local variables what we want. But as I mentioned earlier in the lecture, we know by definition that we have to write a function that takes only one argument. And so the for each is going to call us with one argument, whether we like it or not, right? And if we write a lambda that doesn't, we could call it X or P or Q, but if it was a string instead of a double, then it would blow up, right? It wouldn't work.
Yeah, but when do we enter that I? At what point? Because this looks like you're doing the function right now, like you're about to
Uh,
I'm kind of confused because it looks like you're calling for each, right?
yeah. Yeah. Well, when this executes, yes. So, so maybe I probably should have put a dotted box around this. So consider that for all argument evaluation in C++, we kind of evaluate from the inside out, right? We figure out what each argument is in its own context between the commas, and then we pass what the result of that evaluation is into the for each function. So what we're passing into the for each function is the creation of an instance of a lambda. We're not
Yeah, I
executing
see.
the lambda here, but we're creating the definition of it, and then we're passing that in. And under the surface, it's a functor.
Yeah, I see. I see. I
Yeah,
see.
yeah,
So you're getting double I from all values begin through all values end.
yeah.
You don't enter anything. I see. All right.
So it's confusing because we don't give the function a name. We're not used to seeing functions articulated in this transient way,
Yeah.
but yeah, and it is confusing. I've seen code, again, more in JavaScript or Node on a server side, where people go for a whole page, with equivalently as a lambda, and you're thinking, where is that other parenthesis? I mean, you're scrolling and scrolling and scrolling, and eventually you get to that other parenthesis multiple pages down. There's just some monster transient function that's been defined there, right? So. Good question, though. I'm glad you guys are asking those questions. That's good.
Yeah.
So here's our capture. So here what we're doing is not a big surprise. We're trying to sum all the items, but where are we going to put the sum, right? And what was our initial sum? So we captured the variable sum equals 0 in the beginning here, and we captured by reference so that we can increment that as we go along. So every time we get a new value, we're just adding that new value to the sum. So for each, although it seems like it doesn't allow anything to be passed back, with the use of our lambda here, we're binding the reference to sum, and that's how we return our value, so to speak. But we're basically changing it on every iteration of the for each, right? It's kind of crazy, but it works. So and that's just one variable that we've stored by reference. So we'll see we can use more there. Okay, so that's our summing of values, right? So this is a little different. Think about this one for a moment. This one might confuse you, maybe a little. I mean, these will be on the test in one form or another. You'll see one of these, maybe two. But yeah, so we're going to iterate through. For each is basically just going to call our lambda, and every time we get called, we increment the total by 1. So we're really just counting up the number of items in the container, which is kind of pointless because we could use the container method to do that, but that's kind of our little quiz test, right? So that's what that is. So this is a little bit more evolved. We've captured sum so far as a reference, so it's really just the sum that we saw above, but we're also passing in the mean. And so what we're doing here, essentially, it's a pretty standard statistical thing to do. We're summing the square differences from the mean. And then if we thereafter divide by the sample size, for those of you who took statistics, would give us the variance. I believe that's essentially what we would be doing there. So we're just really calculating a partial statistical value here using a lambda, and we're storing it in the sum via reference. But we needed to pass in some outside number. So we don't know, I mean, we don't really know offhand in our lambda how many what the mean of it is. So we're assuming that gets passed in. Okay. So there's another example for us, right? So any questions on those? And we're going to kind of do this again one more time with accumulate just to make sure this jives, and then we'll move on to variadic stuff, I think, after that. All good? Okay. Okay. All right. Thanks. Hang in there. I know this stuff's a little dry. I know. So here's our picture again. So accumulate. So accumulate, and this goes back to, I think, helps maybe with one question that we had before. So here we want to, we're going to kind of do what we were just faking with the for each in our capture, right? So the accumulate specifically does this for us. It says, I want you to pass me the beginning and the end of the container, an initial value of the sum so far, and then a function. So this is probably, I should have called it my sum function rather than sum, because it looks like it's a variable, but it's a function that's going to just add up two values, right? So it's going to add up whatever it is given, right? A, along with what the current sum so far is. So again, we're just doing what we did on that previous slide, but we have the aid of this accumulate. So it's going to send two things. It's going to send 0 and 12, right? So 0 for the S and 12 for the A. And the sum function is just going to add those two things up, right? And then it's going to send in 9 and 12 because 12 was the previous sum. And then it's going to send in 21 and 7 because 21 was the previous sum, et cetera. So it's sending in two values every time. And we have followed the rules and written our sum function to accept two values every time, right? And we'll look at what our sum function does with those values here in a second. But that's what's going on. So, you know, we had to write sum so that it accepts two values. That's part of the game. If we want to write a function, a worker function for accumulate, we got to follow that function signature. Okay. So let's look at what that function looks like. So this is essentially what's going on there. We're calling that function initially with 0, then with accumulated sum 12, then with 21, etc. Okay. So let's see how that looks from the inside. Okay. I think I covered most of this stuff. So the fourth argument accumulates the argument, or sorry, the fourth is our function that we're accumulating, right? We talked about most of this stuff, so let's get to the meat of it here, right? So here's our vector, sum of squares function. So I can say accumulate vals, begin, and sum of squares. Okay, so I'm just going to add up the previous sum and whatever I'm given by accumulate. Okay, so let's try this. I think I'm throwing you in a little bit at the deep end on this, but I think the samples in the code will help you. You have a sum of squares function. You want to finish its implementation by just returning the sum so far. Okay, so you're going to basically multiply the argument you're given by itself and then return it. That's what we're doing. And the return of our function is actually, in this case, how we populate the sum so far. We don't have to bind anything with a lambda. In this case, we're just going to return a value from our little worker function that represents the square of an argument, and that will get summed up automatically for us. So if you get this right, you should have a sum of 40 the way that code is written. And then if you want to test that again, change your initial sum in main to be 100 instead of 0, so you can exercise that part of that feature. Whoops. And then see if you can get that. And we'll talk about that code. Okay, give that a try. Okay. I'll take a look at the code here, see if I can narrate any guidance for you. So there's kind of a lot of extra stuff in here, which I realize now and looking at this might seem a little, oh wait, oh right, I was looking at the wrong link. Sorry. I'm thinking, why did I write all that extra code? Bear with me one second. This is, of course, another very common, well, the same common statistical thing, summing a bunch of squares. The other one was the difference from the mean, but here we're just summing some squares. And notice in main, when you get to that part, that I've sort of set 0. It's the third argument. You have your begin, your end, and then 0. That's the initial sum, right? We don't have to pass in a variable there. We're just passing in the initial sum. And the return from the function, the return from the whole accumulate function is the sum of all of the stuff that's done by your sum of squares function, okay? Give you just another half a minute there and we'll talk about the code. Okay, let's take a look at it. So I should have mentioned it more clearly. Of course, we kind of switched back to standard functions on this one rather than lambdas, but you could have written the sum of squares with a lambda here, right? And you could have dropped that sum of squares lambda directly into the accumulate function. That would have been perfectly fine. I was just sort of removing a little stumbling block there, but this could just as easily have been a lambda, but we're just getting to know the accumulate function right now. So our sum of squares, what we want to do is just sum up, every item in the vector. We want to multiply it by itself. But if we want to work with the accumulate function, we're going to add that product to the sum so far, and then we're going to return that. And to be clear, I should have put these all in parentheses, but based on precedence, sum so far obviously will get added to these values before it gets returned. But because the plus sign has a higher precedence, so it binds these kind of like a strong magnet. But yeah, that's all we're doing. We are helping accumulate things, right? So we're going to be given the sum so far, and the next value, we'll do something with that. We can sum the values or sum the squares or sum the cubes, whatever we wanted our worker function to do. But accumulate's job is to just collect that stuff as we go along. This is a little strange. It forces you to think about a little bit more indirectly about what's going on when accumulate moves through this list. And then to the last part of that assignment or that practice, if you wanted to start, let's say you're accumulating 1 million values and you want to sort of accumulate them 100,000 at a time, right? And this might be a variable that you pass in that, just so you can restart at some point. So you don't have to count through everything. Let's say if something happens, your process is interrupted. Okay. Any questions on accumulate? Okay. So I think what we're going to do is try to do exactly that, right? We're going to just replace that sum of squares, right? So here's our lambda. I forget exactly what we're going to do here. Let me take a look at this. So this model should be exactly what we talked about, pretty straightforward. We're going to receive 2 ints and then sum them and return them. So go ahead and do that and do it as a transient lambda in this one. I think this will also be quite quick. And think about, how much extra code are you having to write on this one? Oops, too much. Give that a try. I think everybody's got the link there. This should be pretty quick. But I'll take a look at the gotchas and just kind of narrate them out for you as well. So this is our practice number 4. Yeah. So remember, the things that we're going to get is the sum so far, which in this case should be an integer if our vector container is of integers. Yeah. If they were strings, it would be a string, and we maybe were concatenating a string, which would be interesting. And then the second argument is the I argument, right? The particular integer that's coming to us from the container. Okay. And there's a not so subtle meaning here in making you write the lambda twice, right? So to get the point across, it's like, well, yeah, it's kind of a bother to have to rewrite that twice. Maybe we should have named our lambda, you know, or named or created a function, right? We could have done either, but that's kind of the name of the game when you have the utility and the immediacy of those lambdas, but you know, you end up sometimes wishing you had written a function. So let's look at the code just so we can wrap that one up, right? Pretty straightforward, right? So there's our lambda, all buried inside of the parentheses for our accumulate as the fourth argument. Start with 0. Take what is going to be the sum so far, which on the first call will be that 0, and the ith argument that you're given, and then we return the product plus the sum so far, okay? And we're returning it, not just assigning it, because it's not, unlike our first example where we were capturing an external variable, we're actually passing it back to the accumulate function, so it can pass it into the next call. So this return statement becomes the next call, the sum so far when we're called next time, right? That's all. Okay, so that's our accumulate. Okay, so I think that's probably enough on the lambdas. Any questions? Just wrapping those things up before we move into the variadic templates and the variadic arguments. Okay, all right, cool. Good. So I think we're doing okay on time. So these last two are here because sooner or later you're going to be faced with a design decision where you're going to think, man, I really just want to have variable arguments here. Like I don't know how many things I'm going to have to call, and the default argument, you know how we can set defaults on function arguments. You know, that can get us out of a lot of problems, but sometimes we just don't know. And moreover, as we'll see with variadic templates, sometimes we don't even know the types, right? So think of the poor, cout function, right? What if you had to write that function, right? You have no idea how many times people are going to pass in arguments. How are you going to process that thing? If you've ever tried to write a wrapper around a print function, you realize what a pain in the butt that is, because it's like, oh, wow, yeah, of course. You never know how many times somebody's going to feed you an argument. So how do we deal with that? So the reason this is here is because sooner or later you're going to be faced with that. These are not going to be on the final, and I realize, you can kind of tune out a little bit at this point, but as a courtesy, or as a service to you, rather, not a courtesy to me, it's a service to you, I'll try to introduce this so maybe it'll stick in your brains, because I think you might find it helpful. And if you ever run into this syntax out in the real world, you'd be like, what is that thing? So let's talk about variable arguments to functions, like the old, I'll just call this the old way. There's functions that we can use variable arguments in, and then templated functions. And I'll tell you right off the bat, the templated function is going to be the more elegant and modern way to do it, but the syntax is a little mind-bending. So we'll start with just the old school way of having random, or not random, but a variable number of arguments in a function, right? So those are called variadic arguments for functions. They come from the cstdarg library, right? So it's a library that deals with the standard argument pack, right, in function calls, and doing interesting things with those. And the sequence operator, the 3 dots, is not a kind of a me being lazy in my slides. It's a reserved word. It's a key indicator of a special variadic reference. So when you see those 3 dots in the following slides, they got to be, 3 dots. Now the space before or after tends to be optional, but the 3 dots have to be all together. Okay, so let's look at variadic arguments for functions before we get into the templates. So variadic functions, so we want to have a function that has a variable number of arguments. We declare it like so, right? So we have this 3 dots here that says, there's a whole bunch of stuff coming here. I have no idea how many they are. But in the case of functions, they have to all be of the same type, which we'll see in a minute. And I have to preface that here by saying how many are coming, right? So in this particular approach, our first argument is always going to tell the doit function how many arguments are coming. Even though the doit function will be able to handle 100 or 1,000 or 2 arguments, we have to put the number in this approach that we're talking about here in as the first argument, okay? And then, and this is all just in the definition of the function, when we declare it rather, right? So then when we call it, we'd say, okay, there are going to be 5 arguments here, and here they are. They're all the same type, right? And that we'll see how we actually implement the guts of that. That's the variadic variadic function arguments, different than templated functions. So let's look at how we do that. So first off, we have to create an instance of something from the VA list class. So this is a management instance. I'm calling it args, that allows us to manage the arguments that are literally on the function stack. So we just got called. We have to actually go in here and pull the arguments off the stack. And we have this special library that's going to help us do that. And that library has the VA list class in it. So we create an instance of that class, and then we start pulling off a certain number of arguments. See, there's our num args argument off of that stack, right? And we're going to use this VA list thing that we've created to help us do that. So VA start has to be called, and then you can think of it like a string stream or a stack in general. We're basically going to loop through for num arguments, and we're just going to pull off one argument every time. So I'm going to say int this arg equals VA arg. Probably should have been called get arg, but that's what it's doing. It's getting an argument from that args instance of type int, okay? So here is the rub with this approach. We have to implicitly know, it has to implicitly know what the order of all the types are here, so they can pull off an int and then maybe pull off a float or pull off a string. So for those of you thinking about the jigsaw puzzle, this is maybe a bit of a bad example, but the first number in that file was an integer, and then there was a character. You could have pulled off a character next and then pulled off 2 more integers. You would have known by definition for your do it function what the syntax of the file was, and so you could have had maybe some variable number of rows of pieces you could have read in right here, right? So there'd be a way that you could have done it with this, and you could have done it with different types, but only because we would have known ahead of time what those types would be. And so that's a bit limiting, right? It'd be nice to be able to call the function with an arbitrary collection of types that we don't know about ahead of time, right? In this case, we have to know that they're either all ints, or there's an int followed by 2 floats and a character, or whatever it may be, right? So it's okay. And then of course we have to end this here. Otherwise, I think it becomes unstable, if I remember. And that then allows us to do stuff like this. We could say 5 integers or 4 integers based on the way that I wrote this function. Not terrible, it's okay. And you can do some mixed types, again, if you know ahead of time what those mixed types are. But if you don't know what those mixed types are, you haven't anticipated them in your code, then somebody could very easily call your function and give you some random collection of types in some random order that you really weren't prepared for in your code. And obviously, it's going to crash. It's going to pull stuff off the stack in the wrong way. It's not going to make sense. You're going to get garbage data, and maybe even a crash if you're changing data. But this would work for this particular approach, okay? So that's our variadic arguments implementation. A bit old school, but it gets the job done if we stay within the boundaries, the safety boundaries there, okay? In this particular case. So we're going to try that. Any questions on that, by the way, before we dive into that? Okay, so let's do this. This is really very straightforward. I'm really just making you go in and change some types around so I know that you were listening, so that you know you were listening. So go ahead and try to convert this over, instead of being integers, to char star, which is really just the old school string, and see if you can convert this function over to deal with strings. You can pass in some basically char star constants from main. You don't have to declare them as constants. It'll actually work in this case, but give that a try. And then think about, how would you have to rewrite that thing if you wanted to do different types? I mean, I don't expect you to actually do that, but we'll talk about that in a minute when we jump into the variadic templates, okay? So I'll give you a couple minutes on that. Hit me with questions, and I'll kind of look for some gotchas. So again, we're just switching this thing over from int to char star. And we want to basically call it with, some random number, not random, but some variable number of strings. Okay, just another couple seconds. Alrighty, so pretty straightforward conversion, right? So we're really just changing the var args when we're pulling out or initializing or getting an argument rather. We're saying va underscore arg, pass in the args instance, and then we tell it what type. And the reason we tell it what type is so it knows basically how many bytes to pull off the stack, right? It has no idea how many arguments have been pushed on the stack. So we're literally saying, hey, go get a pointer to a character. It's a 64-bit architecture. It's going to pull off 64 bits off the function stack, right? And then we're going to return that to an argument of type char star. So we're just blindly plowing through the function stack and pulling stuff off. And so again, if your code doesn't know what order to pull those things off in or what types they are, things can get mangled pretty badly. But as long as we know ahead of time that, for example, we passed in these kinds of things here, then we can pull stuff off the stack. And as you can imagine, when we pull something off the stack of char star, we're going to walk until we get to a null terminated part of the string there, right? Or rather, I'm sorry, we're just pulling off the pointer. What am I saying? We're just pulling off the pointer, and then when we actually print it, we'll actually follow that printer to the null star. Sorry. So, and the key thing is va end with args. If you leave that stuff out, things get pretty messy. So, and the problem, of course, is that we can't really easily have all the flexibility that we want. So we're going to spend just the rest of the time we have on this idea called variadic templates, which is a better way, but really pretty trippy thing when you really break it apart. We're going to go through it. We're not going to, as I said, it's not going to be on the final, but I just want to walk through it. And we may try one exercise, and then we'll kind of wrap things up for the day. But it might blow your mind a little bit to know that templates can really do this kind of thing. So if you think about it, the compiler is converting our template calls into actual code at compile time, right? So we've seen this kind of thing before where we have a template, right? And Q is a type, right? We're pouring in a type. So we say do it of Q, and if I pour in an int, through these less than greater than signs, Q becomes a type int, and that it literally just rewrites our code for us, right? We've seen that lots of times, right? So that's the kind of idea we want to follow and take advantage of. And there's a little bit of syntax with these 3 dots again that expands that capability to do some pretty crazy stuff. So we'd like to be able to do this, print all, and you see that mixed bag of types. Maybe we want to change the order around so the types are in different orders. And we don't have to want to worry about how many we're going to send in. We just want to list them all the way we use printf or a cout, right? That'd be really nice to be able to do, right? So, and it'd be great if we could find a way with templates to do this intelligently, somewhat recursively. Now, when I say recursively here, I should clarify, I mean sort of recursively at compile time, right? Which probably you've never maybe thought about before, but the templates will actually function in that manner. So we're going to break it down and show that there is a pattern, a way that we can use templates that will allow us to pull this little magic trick off, right? So variadic function templates where we have at least one argument, right? So the way this works is we have a special syntax that says, well, for those of you who have ever dealt with recursion or any other language like Lisp, there's always kind of, or even induction, mathematical induction, there's sort of the first thing that we know, and then there's everything else. We don't know what it is yet, but we know we can process the first thing, and then we know if we could pass everything else down to ourselves and pull off the first thing, we could just sort of recursively process things that way. That's a little bit what variadic templates are like, right? So we have the template expression that says, hey, here comes a variadic template, right? It's going to have a variable number of types in here, right? And so the way we declare our function for that template is to say, oh, okay, well, I know I'm going to have type T as my first argument, right? Which will be told to me at some point. And then the rest, we just don't know what they are, right? So how do I write that function? Well, I do something with my first argument, and then I go ahead and I pass all the rest down to some recursive templatized version of myself, okay? So this is not a runtime recursive call, it's a compile time recursive call. And the compiler takes a look at this special syntax here of these collected value or arguments of these collected types and says, huh, I guess I got to write one of those, right? And so it's just going to keep walking through. It's going to write a function, peel off one, and it's gradually going to chip away at the number of parameters there until it gets down to none, right? And so it's essentially going to recursively write these functions that handle whatever arguments that we pass it in main or something else. Literally at compile time, it's going to say, oh, you want a print all function that has a char and then an int and then two chars and then a string? Okay, I'll write that, right? So it's going to do that for us. And so if our types, for example, in the main, when we called it, were int, float, double, string, where we passed in these values, you know, it's going to have to go ahead and write an int function, and then that handles a collection of these, and then a float function that handles a collection of these. And I'll show you what that syntax looks like, at least to the compiler. But that first argument will always be kind of our var1, or our identifiable item that we can work with, okay? And the only other gotcha that seems a little strange is at some point you can imagine in this recursive process at compile time, we're going to run out of arguments. And we're going to try to call a print all function that has no arguments. Well, we can't do a templated function that way. So we have to write a stub or a final function ourselves that gets called and essentially does nothing, or maybe returns a final value or cleans up or something, or maybe prints ENDL at the end, right? So that would be our termination function. So altogether,
why do we need this strange little?
That's me again.
So why do we need this? So why do we need this strange little?
Okay, good. Moving on to the next slide then. So here is our, the way we call it in main, of course, right? So our blue argument there is our cyan argument rather, is our kind of var1. And everything else is considered the rest. And the compiler is going to chip away at that. It's going to basically print out that first thing and then write something that can take the two and treat everything else as the rest, and on and on and on. So I just kind of broke this down simplistically into these different steps that the compiler goes through writing these functions. Now, if we put all this together, this is what you would write, right? And there's a reference there to a link if you want to see how this stuff works. I've got my kind of stub function up top that I know I always have to write with variadic templates. And then I have this kind of, this is kind of the meat of everything here. I say, look, I'm going to have my first template is of type T. I don't know what it is, but whoever calls me in main is going to have the benefit of determining what T is by virtue of that first function. And then I have this special syntax with the dots before this types here, which is the reverse of down here. But it basically says, okay, and then the rest, right? So a bunch of types followed by the rest of the argument names, all handled by the compiler, right? And it's going to peel off one, do whatever you want with that value, and then process the rest recursively at compile time. Okay. And of course, you could have two types here. You could have T and Q, and then you could do something with two numbers at the beginning if you knew you were always going to have at least two numbers, and then pass the rest down. Or you could accumulate something. There's lots of things you could do there. So here, if we were to go ahead and print out, and this is a little bit of the magic sauce for anybody who thinks they might follow up on this. In Replit or elsewhere, at least in Clang, the Clang compiler, you can ask it to generate the templated code. And I wish I had pointed this out earlier in the semester. But basically, you can do this in Replit in the console window. Just ask it to print out with that syntax. It'll print out all this stuff. And this is kind of what you get. And you can kind of see what it does, right? So there's main, right? That's our main function or invocation. There's our stubbed print all, and there's our kind of chunky, definition of what we want to do with our function. And here's what the compiler writes, right? And it's a bit of strange syntax, and it doesn't execute straight up. So something about the way this compiler option prints this stuff out is not entirely digestible as executable code, which I'm still kind of looking into. But you can kind of see how it's breaking it down. It's saying, okay, I know you called me down here with an int and a bunch of other stuff, right? And it kind of enumerates the other stuff there. It enumerates the types, and then it kind of names them all the same, which is a little strange. And then it calls the functions with what it kind of passed in. And then it writes the simpler version and simpler version and simpler version. So it's really just going to write all these versions for you. And it's not recursive at runtime really, but it's just passing things on to another flavor of the function that's been overloaded essentially, right? So the end result though is that we can, if we want, if we find ourselves in this situation, we can write that kind of function, right? So let's try that. Okay, so this is what we want to do is we want to be able to add some numbers. We call it adder. We want to add an arbitrary number of values. We don't want to have to worry about whether they're integers or doubles. Now we know from experience that we could just declare everything a double, and via precision we get the right mathematical answer. But let's assume for the minute that we didn't have that automatic casting or that ability to do that. So we're going to just add these things up in their, based on their native types. And we're going to use a templated variadic template function to do that. Remember, we have to have a base function adder that has no arguments. That just says, I'm done, right? And we're going to print out, I think we're just going to, are we printing these? I have to look and see what the takeaway is from the exercise. But it's basically the pattern we were just talking about. Oh, right, here we go. We want a recursive adder function to simply add the first argument to the rest, right? So temp sum equals var plus whatever think of it as a recursive call to the rest is, right? All right, and then the temp sum I think we're going to return, right? So here's the function we want to write. I think the base adder is written for you, and so you're just really going to need to create a temp variable in there called temp sum and add that. Kind of dig around in that syntax a little bit just to get familiar with it, okay? And then go to main and try to just print out a sum of the various different arguments that you pass in, okay? And think about the final type. We'll talk about that in just a second, okay? This will be our last one. So take a look or hit me with questions. I'll look at the code and just see if I can narrate any gotchas as we go. I probably should have put a little hint for you there, but one gotcha you might have, you might run into, is when you use the rest and dot 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 right in your function calls, the dot 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 is going to follow the rest, and there's no comma between those. It's kind of thought of as a parameter pack. So when you say the rest or whatever template name you chose for that pack, you're always going to put the dot 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 right after that. Okay, another half a minute maybe. Let you mull over that last question there. It is kind of interesting to think about what does return the type here. You kind of have to think recursively, even though what all these functions that get written is just like a stack of overloaded functions. Think about which one's return value, has effect on the final value. There's the magic sound. Okay, let's wrap this one up then. So, oh right, we don't have the code. Why don't I have the code here? Oh boy, oh boy. Let me see if I can swap us over, because I do think it just doesn't do us service if we don't. Can I give you a view of the code? So let me see if I can swap you over quickly, and then we'll get you guys out of here. So I'm gonna go there. I want to go to, hard to know, I got so many replets open. This one, maybe. I'm lost. Where did it go? Sorry, guys. I'm trying to figure out where my share went. Hold the phone. I think I may have to give that up. Were you guys seeing anything? Maybe not. Okay, I'm going to go back to the slides. Sorry about that. I think basically, if you want to take a look at that, you might want to click into that solution. But essentially, because we're kind of calling, the stack of functions, the basically the top level function is going to determine the type, and that's always going to be the first argument. So if our first argument was an int, we're going to end up returning an int, because all these things are going to be added ultimately into an integer typed variable, which is determined by the var1 t type in our template, and that's going to be our final result. So that's variadic templates. If you only remember one thing, remember that there are two ways, or maybe two ways to actually manage variable arguments and functions inside of C++. You can do it kind of the old school way with the C standard arg library. It's a little bit constricting. Or you can do it this way. It takes a little bit of brain power to write these things, but once you do, they're incredibly powerful using this variadic templates. Okay, so that's kind of it for the day. Wraps up our kind of advanced functions module. When we meet on Thursday, we're going to talk about assert and exceptions, try, catch, and throw, which many of you may have heard of, but may not have done anything super elaborate on. But we'll talk about the philosophy of that system and how it actually works. And that will be on the quizzes in the final. So I want to give you ample time to go through that. Other than that, I know we're still wrapping up homework 8. Some of you have started on 9. You still have 2 full weeks on 9. Remember that, and 2 full weeks if you decide to do 10. But I will be here for the lab to answer any questions. Otherwise, have a great week, and I will talk to you guys all on Thursday. Okay. Thanks all.